We've talked about Bayesian approaches to model selection, and we also talked about cross-validation, which was a non-Bayesian sort of approach to model selection. And I'd like to give you a list of some of the other popular model selection techniques that are out there, or ones that you may have heard of. So the first one is the AIC, so-called AIC, and it's I have no idea how to pronounce this, a K-key, I guess, information criterion. And the closely related BIC, or Bayesian, so-called Bayesian information criterion. And these are very similar. And the idea behind these is that you penalize models according to the number of parameters that they have. So if a number has more parameters, the idea is that it's a more complex model, and it's more flexible. It can handle more different types of data, and so the model complexity is higher. And you should penalize models with more parameters so that they have to really make up for it in terms of how well they describe the data. So these sort of penalize in terms of the number of parameters. And another approach, which is closely related in some sense, is MDL, or minimum description length. And this is a very oversimplified. So what I'm going to describe is a very oversimplified version of MDL. MDL is actually sort of a fairly large field of research, but MDL, the basic idea behind it, well, if you were applying it for model selection, is that you want to choose a model which has the smallest description length, and it's using description length as a measure of, or as a proxy for, the complexity of the model. So this is sort of the Occam's razor principle. Occam's razor, which is that you choose among equally valid alternatives, you choose the simplest explanation. And that's the idea behind MDL, the basic idea behind MDL. So all three of these, I'd like to sort of lump these all together and say that all three of these share a lot in common with one of the Bayesian approaches that we talked about. Remember, one of the Bayesian approaches we talked about was maximizing. I called it type 2 MAP, type 2 maximum a posteriori estimation, where we wanted to maximize the probability of a model given the data. And this is proportional to, I think we wrote this down in that video, proportional to the with respect to m, that is, proportional to the probability of the data given the model times the probability of the model. So if you took the log of this thing, well, I don't need to take a log twice, log of the probability of the model given the data. Of course, maximizing the log is the same as maximizing the original thing. That's equal to the log of the probability of the data given the model plus the log of the probability of the model plus some constant. And so these sort of, explicitly AIC and BIC take this sort of form. You're trying to maximize an expression of this form. This is like some log likelihood thing. And over here, they have each of these has an expression which is sort of essentially you could view it, if you were thinking from a sort of from this perspective, you could view it as putting a prior, or maybe in some sense it might not be a proper prior, but at least some sort of even maybe improper prior over models until you get some expression here. And you want to maximize this guy. So these can be viewed as essentially this type 2 map that we talked about in Bayesian model selection techniques. And minimum description length, if you were to formulate a minimum description length criteria for doing model selection, then you would do something like this, where this log of the probability, and in fact this is what people often do, the log of the probability is formally equivalent to a description length in some sense. Formally speaking, you could formally represent a description length. Actually, I guess I should say minus, so you would say minus the log if you we wanted to maximize this. So if you were minimize, that would be the same as minimizing minus that, and minus the log of a probability. There's a formal connection between minus log probabilities and description lengths. And in information theory, that equivalence is very, very heavily used. So I just wanted to mention that all three of these can be viewed as sort of equivalent to that type 2 map. Okay, so that was those. And another one, I guess there's only one other one that I wanted to mention. So another sort of technique that people use for model selection is what's called the VC dimension, or the Vapnik-Chervonenkis dimension. And it's beyond this video to describe in detail what the VC dimension is. Let me just write here. Vapnik. I don't know if I haven't written it down. Chervonenkis. Let's see if something like that. I may have spelled that wrong. Spelling. The Vapnik-Chervonenkis dimension. Chervonenkis dimension. And very roughly, let me just give you the rough idea behind Vapnik-Chervonenkis dimension. The rough idea is that you penalize models which can, so this is specialized to classification, and you penalize models that can separate more complex data. So I'm not going to say more than that, but just the basic idea is that you penalize models which can have more sort of wiggly decision boundaries. So if they can separate lots of different types of data sets, then they have higher VC dimension, and so you would if you were doing model selection using this, you would favor models that are less complex, that have sort of less wiggly, that can have less wiggly decision boundaries. Okay, so these were just a few I just wanted to mention in case you've heard of these other things, to sort of understand at a very, very high level, a very rough idea of what these are doing.